We're continuing and finishing our discussion of chapter 9 then today by looking at metallic zinc. So our previous lecture, we talked about some of the different kinds of flammable metals and flammable solids. We ended with that thermite reaction in at the very end, talking about how we get molten iron out of a combination of aluminum and iron oxide. Now we talk about zinc. Zinc is a metal that is in a lot of places used as a corrosive anti-corrosion agent for iron. If you've heard of galvanized steel, that is basically steel, iron, and carbon and some other things that has been doped and added zinc to it. It gives the steel kind of a silvery kind of look. We know that zinc and copper are also used to make brass. So zinc has a lot of applications in metallurgy. We also find it used in dry cell batteries. Zinc itself is not corrosion proof. In fact, zinc reacts very, very well with concentrated acids. However, it is also a very, very good electrolyte in terms of its ability to go from zinc to the ionic zinc, zinc 2 plus, is quite significant. And as a result, it's often used as the anode in batteries. And dry cell batteries are one of those examples. Now, on their own, zinc in its bulk form, if I took zinc turnings or mossy zinc, probably wouldn't catch on fire. But in its dust and its powder forms, it is said to be pyrophoric. Again, the big difference here is in surface area. The larger the surface area, the more likely it is to be highly reactive. Also in this category of substances that are flammable, we have the metallic hydrides. Metallic hydrides are kind of interesting. For the most part, we think of hydrogen as going to the hydrogen plus ion. We've seen this in most of our cases where hydrogen acts more like a metal and taking on a positive charge than a non-metal. And we've seen this in things like hydrochloric acid, sulfuric acid, nitric acid, and so on. Hydrides are the opposite. Instead of hydrogen turning into a positive ion, we get hydrogen turning into a negative ion. And metals, because they have positive charge, will react with that hydrogen ion, that hydride ion, to make some pretty considerably powerful agents, because hydrogen minus is not the preferred mode for hydrogen. It would much rather be hydrogen plus or hydrogen with no charge at all. And so as a result, these can be very, very powerful reducing agents where they will end up giving that extra hydrogen away to something else and cause it to be reduced, cause the hydrogen to be oxidized. So in these, we have simple metallic hydrides. We're looking at things like sodium hydride, NaH, calcium hydride, CaH2, and so on. We also have in here metallic borohydrides, where we incorporate boron and hydrogen along with a metal. And there are also complex aluminum hydrides where we've got aluminum hydride, AlH3. It's kind of the backbone to a larger, more complex kind of molecule. So under the simple ionic compounds, again, we're talking about hydrogen acting as an anion, hydrogen in the negative state. And to this end, we get some substances that have these kinds of chemical formulas. Mentioned a few of them on the previous slide. These hydrides are highly reactive because, again, hydrogen doesn't care for the -1 state. It can take it, but it would much rather be 0 or +1. So with that extra electron being stuck on it, it's going to want to get rid of it very, very quickly. And as a result, these substances are usually very, very reactive with water and very, very reactive with other substances as well. When they react with water, they will produce hydrogen gas. So basically, we've got the hydride ions turning into hydrogen. And we've also got the water molecules turning into hydrogen as well, and usually some hydroxides. Because of their reactivity with water, we will often see them sealed in containers, try to keep them airtight, try to keep them from the moisture in the air. We'll often see them covered in things like petroleum oil or mineral oil. And their fires, because again, we're dealing with hydrogen gas and the potential flammability of hydrogen, dry powder is basically the way to go. Carbon dioxide doesn't do a good enough job, blows around the hydrogen a little bit too much. Dry powder kind of smothers everything, keeps it all contained. Another group of highly reactive but unusual compounds are carbides. Carbides are, we've talked about carbon in a number of our units, chapter 4 in particular. We talked about how carbon does not tend to form ions. It's much more prone to molecular covalent bonding because it's got those 4 unpaired electrons. And to form an ion, it's going to have to either gain 4 electrons or lose 4 electrons, and neither of which is all that good. But it is possible to take on a charge as carbon. And the 2 primary components, the 2 primary reactants, are aluminum carbide and calcium carbide. Aluminum carbide and calcium carbide, when they react, these are both water reactive. And when they react with the water, they will end up giving flammable materials as a result of their reaction. So in aluminum carbide, we have Al4C3. In calcium carbide, we have CaC2, which is kind of odd because that this one's always been kind of puzzling because the calcium carbide, what that means is that it doesn't actually form a positive 4 reaction state or a negative 4 reaction state for the carbide. It is very odd. But what is interesting about these is their reactions will give us flammable material. So how do we make them? Well, aluminum carbide is made by taking aluminum oxide. Aluminum oxide is basically the dull grayish stuff that is on the backside of aluminum foil. So if you ever notice, aluminum foil has kind of a shiny side and a dull side. The dull side is the corrosion resistant side. That is the aluminum oxide. So you take that aluminum oxide, you put it into a furnace with carbon. That's what we refer to by coke. Coke is a carbon-based product that is used in the steelmaking industry. And you heat it up together, and what happens over time is that the carbon will slowly replace the oxygen inside of the aluminum oxide. When it reacts with water, what we end up getting is natural gas, CH4. So that's the one kind of reaction. The other reaction, calcium carbide, again, we get it through a mixture of coke, but we also get lime in there as well. Lime being calcium carbonate from limestone. So the combination of calcium, carbon, and limestone, heated up in an electric furnace, we get the calcium carbide as a result. Calcium carbide is much more reactive than the aluminum carbide is. Calcium carbide can react with the humidity in the air to produce a relatively combustible, nearly explosive kind of material. So use of calcium carbide has to be very, very well controlled. When it reacts, it forms industrial grade acetylene, C2H2. And so the reaction that we get ultimately, calcium carbide reacting with water, we get acetylene, and we get calcium oxide. Now, you will do a lab after our hiatus where you'll actually get to do this reaction. But we're going to do it in kind of an interesting and different way. We'll use ice as our reaction medium instead of pure water. The reason for that, ice is at a lower temperature. We create less water over time because we have to wait for the ice to vaporize or melt. And so as a result, we get a very slow kind of production of acetylene. But what ultimately happens is the acetylene will form these little bubbles inside of our evaporating dish and take a burning splint or a long match to them, and they will just start popping these little fireballs inside of the hood. It's kind of a cool demonstration. So that's on the metal side. On the non-metal side, we know that we have a number of substances that are reactive with oxygen. When they do, through these combustion reactions, we get a series of substances that are reactive with water and will form acids as a result. So here we have, kind of a twofold problem where in addition to In addition to the first problem of having something that is combustible, the resulting oxide product also forms a corrosive, in this case, phosphoric acid. In other cases, things like sulfuric acid, nitric acid, sulfurous acid, a number of substances that have been associated with industrial runoff and pollution, which are ultimately responsible for things like acid rain. Of these substances that are non-metallic and also have these other kinds of combustible issues associated with them, probably the most notable in terms of their reactivity and in terms of their danger are phosphorus and sulfur. So we'll examine each of them in turn. Phosphorus. Phosphorus comes in a number of different varieties and different forms. When an element is said to have different varieties or different forms that naturally occur, we call those different forms allotropes. You're common with the allotropes of carbon, for example. One of them, most of you are using right now, graphite. That is probably the most common and the most stable form of carbon. Graphite is used in pencils as the quote unquote lead that allows you to write. Graphite is soft, which is why when you use it on a surface like a piece of paper, it smears instead of poking through it or scratching it. Diamond, on the other hand, comes from a different configuration of those bonds to each other and is a very, very hard substance that will scratch pretty much everything. It's one of the hardest substances known to man. It might, in fact, be the hardest substance that is non-synthetic. Now, for phosphorus, there are two common allotropes. There's the white phosphorus, which we mentioned in passing before. This is the stuff that is pyrophoric, reacts instantaneously with air to give very, very hot fire. As I mentioned back then, it was and still is in some places a chemical weapon agent, although it's been banned for some time. And then there's the red phosphorus. Most of us are familiar with red phosphorus. It's the stuff on matches that gives the match head its red color. Now, those two substances actually interconvert between each other. White phosphorus, as you might imagine, is the less stable form because it is so much more reactive. Under normal conditions, it will gradually change to red phosphorus. And in fact, the yellow coloration of white phosphorus is a result of some of that interconversion taking place. So trace amounts of phosphorus inside of the white phosphorus sample are turning red. And as they transition from white to red, the process gives a kind of yellowish orange appearance to the whole sample. When phosphorus comes into contact with air, it is pyrophoric. It will instantaneously burn brightly, and burn without an external ignition source. The resulting substances as a result of that are toxic. They can cause severe liver damage when they are ingested. This is the most lethal and the most unstable form of phosphorus. What we've got going for us, it doesn't dissolve in water, and it doesn't react with water. So when we have white phosphorus samples, and there are still some around there, they are largely stored underwater as a safety measure. When white phosphorus is transported from one area to another, it is kept in a heated container in its liquid form, which does provide it some additional stability. Prevents it from, at the very least, needing to be contained and preventing it from being jostled around in water or something like that when it accidentally can fall over and become ruptured and explode. Red phosphorus, on the other hand, is a dark red color. Now, there is a third form of phosphorus that is called violet phosphorus. Violet phosphorus is pretty rare, and it's actually also less stable than the red phosphorus. So violet turns into red as well. It is not pyrophoric. It will not catch fire in the air, but when friction is applied, it will burn. And so that's where its use as a match head comes into play. Friction is what causes that match head to ignite. The phosphorus on the match head can get enough energy to kickstart its combustion just by rubbing against something else. And so where we see it most often, flares, safety matches, those little cap gun caps that are put into toys. And well, unfortunately, it is also used in the production of street drugs, most commonly methamphetamine. Sulfur is an 8th sulfur compound, so it naturally exists in this crown-shaped ring. As a result of this crown-shaped ring, we actually get some really kind of cool crystalline forms that come out as a result. The sulfur actually forms these large crystals that are rhombus shaped as a result of this ring. In its crystalline form, it is yellow, it is hard but brittle, and it has a very, very slight odor. Now, most of the time when we think of sulfur, we think of very powerful and strong odors. We think of things like rotten eggs or burning tires, burning hair. But those are not sulfur themselves. Those are sulfur-containing products that happen to have odors associated with them. Hydrogen sulfide gas, in fact, is what smells like rotten eggs. Sulfur dioxide gas is that strong reaction that comes with burning hair, burning tires, burning anything that contains sulfur in it. But sulfur itself, as an elemental substance, doesn't have much of an odor at all. And we certainly wouldn't describe its odor as being strong or powerful or stinky. It just has a very, very faint kind of smell. Where do we find it? We find it near hot springs. We find it near volcanoes. We see it especially in high quantities in the Ring of Fire around the Pacific Ocean. Sulfur does not take a whole lot of energy to melt. It melts around 100 degrees Celsius. It easily sublimes. When it sublimes, it often will catch fire. When it catches fire, it'll give us a blue flame, kind of a dark royal blue color, and a whole bunch of sulfur dioxide gas. Again, sulfur dioxide gas is the stuff that smells like burning hair. Sulfur is also a component in black powder, which itself is a mixture of saltpeter, potassium nitrate, and charcoal, which gives it its black color, and sulfur. Sulfur does not dissolve in water. It is not a toxic element on its own, so it does stand apart from phosphorus in that regard. But that doesn't mean I'm going to sit around and eat a whole bunch of it. Where we have to be the most careful with the sulfur is, again, because it has a relatively low melting point, it does vaporize very, very easily. It does catch on fire at relatively low temperatures. All right, we've got one last class of materials to talk about for this particular chapter. And they all surround a group of compounds that will make acetic acid when they react. Now, there are a number of compounds that do this. Why is acetic acid so important? Well, because in acetic acid, we have an organic acid. That organic acid usually is derived from other organic products that have their own sets of hazards associated with them as well. In addition, acetic acid has a very strong odor. That is the odor of very highly concentrated vinegar. And if you inhale too much of it, it can kind of give a suffocating effect. It also can irritate the heck out of your eyes and your nose. So what kinds of compounds do this kind of a reaction? Well, the first and foremost is something called acetic anhydride. Acetic anhydride has a lot of commercial uses. This is used to make a number of different products. So this is a precursor to aspirin in the aspirin making process. This is also used to make cellulosic films and other kinds of products. When it comes into contact with water, basically it's going to split down the middle here and make two different acetic acid molecules. And so from this substance, which really doesn't have a whole lot of, it has odor to it, but not nearly as strong as the vinegar odor. We do get a lot of reactivity from it. Acetyl chloride, also a colorless fuming liquid. It's used in the chemical industry as a precursor for a lot of different chemical reactions. And when it reacts with water, we end up getting a couple of things. We end up getting acetic acid. We also end up getting hydrochloric acid as a result. So with acetyl chloride, we've got this chlorine group. This chlorine group is highly reactive. And when I put it into water, I get hydrochloric acid. And I also get the acetic acid that we've been talking about here. Reaction here, most of the reactions with acetyl chloride are violent. They're very, very robust. This is a very, very prominent reactive organic molecule. So any kind of acetyl halides, but chloride being the most common of them, are pretty reactive stuff. But the real kicker in this one is actually the hydrochloric acid. Getting vaporized hydrochloric acid is pretty dangerous because in that vaporization, you've now got a medium for that hydrochloric acid to go out and do some pretty corrosive stuff because it is such a strong acid. And then you couple that with the pungency of the acetic acid product that's also made, it's a pretty nasty reaction. For these kinds of fires, obviously we can't use water with them because they're water reactive. We have to use carbon dioxide or dry chemical. So we've got to use something in the BC range. We also, because of the vapors, we've got to use protective clothing because the vapors will corrode most kinds of fabrics. And it's a good idea to wear a self-contained breathing apparatus as well because the vapors are corrosive to your body and will cause some pretty significant pain to your nose, your throat, and your lungs. Because of their water reactivity, again, we cannot use water as a fire extinguisher. We have to use some other kind of dry chemical agent or carbon dioxide. And so that is it for chapter 9 here. Like I said, chapter 9 is a relatively short one. We were talking mostly about things that are flammable, things that are are going to create vapors or are going to be water reactive. And really, the water reactivity is kind of the most scary one, because being water reactive means that we're also going to run into some issues with being able to fight any kind of fires that we would encounter, because it limits our options. And anytime our options are limited, we have to be extra careful because of what other kind of ramifications come about. All right, really good stuff in here. So we start now by looking at chapter 10. Chapter 10 focuses on the toxic substances that exist. And we're going to be looking in particular at the chemistry of some of those toxic substances. So to that end, what we need to do first, before we get into the actual substances themselves, is we've got to define some terms. And we're going to start by defining what toxic substances are and what we can do as far as the study of those substances. So we begin by just defining some terms. First of all, we define toxicology. Toxicology is simply the study of toxic substances. We also look into epidemiology. Now, epidemiology has become a term that has become more and more prominent in the last year, mainly because of focusing on this end of epidemiology, the study of diseases. But epidemiology can also study the effects of toxic substances on people. And so, while in this age of COVID, we have talked about the epidemiology of the coronavirus, and in particular, the SARS-2 coronavirus variant, toxicology and epidemiology do also come into play for other kinds of human population, I don't want to say disasters, but issues that have come up. You think about going back to 2001, the great anthrax scare following 9/11, or going back even about 10 years ago, the ricin scare, where ricin was found in a couple of letters sent out to, I believe it's a couple of senators. Anytime we get into the toxic nature of substances and whether we are dealing with a localized problem, as was the case with ricin, or a more national problem, as is the case with anthrax, we have to look at what are the population dynamics? What kinds of things do we have to concern ourselves with as a people, as a nation, or as in the case of COVID-19, as a human population in the world? Now, when we do those kinds of studies, one of the things that we have to look at is how does the toxin find its way into the body? And there are three primary ways that toxins can get into your body. The first of which, probably the most common, is ingestion. Ingestion involves you, well, eating something. Taking something that is toxic, swallowing it through your mouth and into the digestive system, and from using the digestion system and the bloodstream, that gets out to your organs, the rest of your body. The toxin spreads kind of internally in that manner. What we will find is that all three of our toxic substance modes of entry are going to end up going into the bloodstream in some way or another. The quicker the toxin gets into the bloodstream, the faster the toxin tends to work. So ingestion is kind of a slow methodology, because when you eat something, it can take hours for your body to digest it, move it through to your intestines, from your intestines, it goes out to your bloodstream to the rest of your body. Now, there are some notable exceptions to those kinds of things. For example, cyanide Cyanide can have that effect. But one of the things that happens with cyanide that is different is cyanide becomes vaporized in your stomach because it becomes acidified, and you end up getting it from two ends, which is why cyanide usually works a lot faster. So the first mode is ingestion. Again, to go through ingestion, it has to go through your digestive tract and ultimately gets disseminated into your blood through your intestines. Another common way is skin absorption. This is where the toxic material literally gets absorbed by your skin, finds its way into your bloodstream through your skin. This is less common than you think. There are very few cases where absorption is actually the primary mode of transmission, but it is possible. Where we see this is for things like mercury. You break a mercury thermometer on the table and you try to blot it up with your bare hand and a paper towel because it's a liquid. That mercury can get seeped through the towel into your skin, and you can end up getting mercury poisoning in that kind of way. There are other kinds of toxins that do similar kinds of things, but that's probably the most common example. And the reason it exists is because your skin has direct contact to your circulatory system. Once it goes through the epidermis and into the dermis, it is going to come into contact with blood vessels. And those blood vessels are going to be able to carry the toxic material to the rest of your body through the pumping action of your heart. Of the three, inhalation is by far the most dangerous, because inhalation is going to involve some kind of a gas being brought into your lungs, and your lungs then disseminating that toxic material to the rest of your body. So inside of your respiratory system, you have your alveoli. The alveoli have a direct barrier to the bloodstream. That is how your blood gets oxygenated. That's also how your blood becomes decarbonified through that exchange of gases in your lungs. And so if you inhale a toxic substance, it's usually pretty difficult to get it out because it gets into your bloodstream very, very quickly. And so, again, what we can see here, when it comes in through your nose and mouth, it ends up in your respiratory system, your lungs, and in particular, your alveoli connect the lungs to the bloodstream. It can get into the bloodstream very, very quickly because every breath you take exchanges materials inside of your blood. Carbon dioxide comes out, oxygen goes in, we exchange gases, and if there are other gases present in there, they can get exchanged into the bloodstream as well through the alveoli. And that's where we'll stop for today.